Let's explore where the expressions for hydrostatic equilibrium and buoyancy come from in your lecture notes. So if we consider some region of fluid and isolate a little part of the system that has some density rho b and some volume v. Well, what are the forces acting on this little region? There's a force from the top, caused by the pressure of whatever's sitting on top of it, but there's also a force from the bottom caused by that pressure. Unlike a lot of forces that we deal with in physics, pressure is often isotropic force, meaning that it pushes in all directions equally, so that's why at the bottom of the ocean you don't just get pushed down, you get crushed from all sides. Don't go to the bottom of the ocean. There's one more force that people sometimes forget about, though, which is, assuming this is in a gravitational field, the force of gravity acting on the little box itself. Okay, so those are our three forces. We'll define the positive z direction to be upward and proceed with our calculation. So if we draw a free body diagram, it's just going to be those three forces as we've already represented, and the net force is just the sum of those three forces. Pressure, however, is a force per unit area, so we can actually rewrite the force on the top of the box and the force on the bottom of the box in terms of the pressure at those two locations and the area of the top of the box and the area of the bottom of the box. If we do that, well, F top is going to be minus P top times A, where the minus sign just indicates that it's a downward force. Force at the bottom of the box is going to be pressure at the bottom of the box times the area, again with the sign indicating the direction. I'll assume in this calculation that the area of the top and the bottom of the box are equal so that we don't need a subscript on the area. So if we put that all into our expression for the net force, we get that the net force is minus P top times the area plus P bottom times the area minus rho b vg, where that last term is just a modified version of the force of gravity. Rho b times v is the total mass of stuff in the box, and of course minus gives the direction, little g just converts the mass into a weight. We can pull out a factor of minus a just to clean this up a little bit, and now what we're going to want to do is to rewrite this in terms of the position of the top of the box relative to the position of the bottom of the box. And fortunately, we can rewrite that volume term v in exactly those terms by saying that v equals the area of either the top or the bottom of the box times the difference in the two positions of the top and bottom of the box. That's just saying that the volume is the area times the height. So if we do that, we substitute that back into our net force expression, and now we have this rather long expression. So far we haven't made any assumptions about equilibrium, so this is still a general expression for the force on that box. But if the system is in hydrostatic equilibrium, what that means is that this net force must also be zero. So the left-hand side of this equation becomes zero. And now we just have 0 equals all of that other stuff. So moving this up, we can rearrange this a little bit into something cleaner. So the difference in pressures equals minus rho times the difference in positions times little g. And we can rearrange that into a fractional difference now between pressures and positions. If you've taken calculus recently, you might recognize what I'm trying to do on the left-hand side. Let's consider the case where this becomes an infinitesimal positional difference, so that z top is very, very close to z bottom and their difference is very small. Well, we can rewrite the left-hand side as the derivative dp dz. And that's the full expression for hydrostatic equilibrium. So for a system in hydrostatic equilibrium, this equation should hold at any location in the system. Now that tells us about hydrostatic equilibrium. How do we go through and relate this to the buoyant force? Well, we're going to use this to actually determine what the pressure is in the ambient medium around an extended box. So for hydrostatic equilibrium, we had to assume that the box became infinitesimally thin. But more generally, we can figure out what the buoyant force is on an extended object just by using this to compute the pressure in the ambient medium, which is presumably in hydrostatic equilibrium. Let me show you what I mean. So let's rewind our derivation a bit and go back to the beginning. We're actually up here, we hadn't assumed anything about equilibrium, so we'll blank out all this stuff. These first two terms in our net force are what is called the buoyant force. So it's just the sum of the forces on the top and bottom of some object like a box. And those correspond, of course, to these two terms in the lower expression. So let's call that the buoyant force. So F buoyant equals minus A times the pressure at the top minus the pressure at the bottom. Our goal now is to compute the difference between the top pressure and the bottom pressure using the condition of hydrostatic equilibrium in the ambient medium. So if the ambient medium is in equilibrium, and we know that it has a density, we'll call it rho sub A, then we can say from our previous work that dp dz must equal minus rho sub A times g. So again, that's hydrostatic equilibrium applied to the ambient medium outside of the box. But that'll help us figure out what the pressure at the top of the box and the pressure at the bottom of the box are. So it's that density that goes in, not the density of stuff in the box. We can rewrite the derivative as a ratio of differences, and I can get away with this as long as I'm pretty sure that rho sub A and g aren't changing appreciably over the size of the box. If they were, we would have to keep it as a derivative and formally do integrals, but in this case we're pretty sure that whatever the ambient medium is, if it's water, it's probably about the same density at the top and bottom of the box, and certainly little g wouldn't change much for a box of reasonable size. So moving everything up, we can solve for the difference between the two pressures, P top minus P bottom. It's all that stuff on the right-hand side. And the whole point of doing this was so that we could insert this expression for the difference in pressures into our initial expression for the buoyant force. So let's do that now. Buoyant force becomes minus A times the quantity minus rho Ag times the quantity Z top minus Z bottom. Well, you may recognize actually that if we rearrange this a little bit, the area times the difference in heights is just the volume of the box, right? So we can rewrite this bit as the volume of the box and conclude that the buoyant force must be equal to rho sub A times little g times the volume of the box. Just to be absolutely clear, this is again the ambient density, so the buoyant force in the box is actually determined by the density of stuff around it, which we now understand because ultimately it's the difference in the top pressure and the bottom pressure that are really causing the buoyant force.